Alrighty. What I'm gonna hopefully this will be a little short video. We want to talk about de Broglie because you can't really get through quantum mechanics without talking about de Broglie. Uh, he was a French physicist in the 1920s. Got a Nobel Prize in Physics in 1929, and he did contribute into this quantum mechanics business that we're deep in the weeds of at the moment. Okay, so at the moment, physicists and even Bohr, it was Bohr's theory put together this whole energy level business, right? But even Bohr was confounded as to why electrons might be limited to only having certain energies and why they only orbit at fixed distances. Okay, so de Broglie comes in and looks at this and comes up with some interesting ideas. But first, let's think about this. Let's think about standing waves. Um, just to get us under uh, get us this idea here. So standing wave has fixed endpoints. Okay, so you can think of this like a guitar string, and you pluck the guitar string and it vibrates, but the wave doesn't really go anywhere. It stays in the string. Okay, that's what we're thinking about here in terms of electrons in their waves. Okay, so, well, I'm jumping ahead of myself. So if we have a wave that goes in a circle, like an orbit, right? It looks like this. So we can picture it like this. This is some distance from the nucleus. All right. Right. Because our standing wave has fixed endpoints, it can only vibrate at certain frequencies because you have to have a whole number of wavelengths. That's what we're getting at here, a whole number of wavelengths. Okay. So only certain frequencies and certain wavelengths will work because you have to have a whole number multiple of wavelength segments within that. Okay. So if you think about this wave now in a ring or a circle, right, you only have a whole number of wavelengths, it matches up as it goes around. Okay. That's what this guy's doing. It's matching up as it goes around. I can't draw in the GIF at the same time as stressing me out. Okay. If you don't have a whole number of wavelengths, then at some point when the wave meets itself back up around to the other side, they don't match up. And now you have your destructive interference, right? So this is what is happening when we say, okay, you have to have the allowed amount of energy, because if you don't, you're going to crash into the nucleus. Okay, so here we're saying that it's a whole number of wavelengths, because if you don't have a whole number of wavelengths, then you end up canceling your wave out at points. Okay, so de Broglie took Einstein's idea of saying that if light can act as particles and as waves, then why can't electrons that are particles also have wave-like properties? Okay, and he took it a little bit further and said anything that has mass can have wave-like properties. Something that's moving that has mass has wave-like properties, and that's a little bit weird, um, but it works. So his argument was that electrons behave as standing waves, and that's why we have to have a whole number of wavelengths going around here. What's next? Okay, yeah. So what he came up with is to say that, okay, the circumference of this loop is 2 pi r, and this has to equal some number n times the wavelength, where n is this integer, okay? R is the radius. I should write these down on, oh crap, sorry. Should write these down on here. This is the radius, right? Because this is the circumference, right? Around the circle. N is an integer. You'll recognize this n over and over again, right? Lambda is our wavelength. Okay, so if we have some sort of integer multiple of wavelengths, we can have a full circumference around the circle. Okay, and so Uh, yeah, de Broglie went ahead and defined. I keep changing the slide. I'm sorry. Came and defined this as a de Broglie wavelength, and said that the wavelength is equal to Planck's constant divided by the mass of the particle times its velocity. So this is mass. We're not going to do anything with this. Okay, just kind of putting it out there. That's our de Broglie wavelength idea here. But again, we want to think about we have to have a whole number multiple of wavelengths to go around. Okay, so how do we know this is what's happening when we look at electrons and we look at light? Okay, let's look at some experiments. Um, if we look at this, okay, don't look at this side first. I should have made a pop-up or something. Okay, so over here we have what we expect. If electrons are being particles and we fire electron beams at a slit, so this is our double slit experiment again, we should see two spots where the electrons hit, and they should be lined up with where the slits are over here, okay? When you do this experiment with actual electrons and you fire electrons at the slits, what you see is the interference pattern. So they are diffracting like waves, okay? Here they're acting like particles. Well, the particle beam would look like that. So the electrons are acting like waves. I'm sorry, I'm getting my brain just paused. I'm sorry. Okay, here we go. So the electrons are acting like waves, which is good because it helps solidify de Broglie's position about the whole number of wavelengths going around in a circle. All right. So if you modify the experiment and you now say, okay, I want to see where these electrons are coming out as. So you put a laser on the other side of the slit and you say, okay, the laser is going to let us know every time an electron goes through it. So we know when the electron goes through the slit. Okay. Well, if you measure where the electrons are, now the electrons are acting like a particle and not like a wave, because now we're getting two bright spots and not the interference pattern. If you stop measuring where the particles are, now they behave like waves again. And so there's this duality of wave properties and particle properties, and it all depends on how you're measuring the experiment. Okay, I love this meme I found. I don't know, remember where I found it years and years ago, I guess. That if you're not looking at it, it looks like a wave. If you're looking at it, it looks like a particle. And so you have to, this is a problem because how you set up the experiment dictates your results, right? A lot of determining where an electron is involved with giving the electron more energy and seeing where it moves to. Okay, so if you want to know where the electron is, you have to give it energy to measure it. But when you give it energy to measure it, the electron moves. So this is a problem. Okay, and this kind of opens the door for more experiments and more explorations. I guess I was going to write more stuff here and I just didn't. All right, that's it for de Broglie, and I'll see you again later.